All right, thanks a lot for that. Yeah, so cutting edge football analytics. I have to say it's probably cutting edge open source football analytics, but I'm doing my best. We're going to use Polars, Keras, and Spektral, and what those packages are I'll explain in a little bit. Well, Polars and Keras are probably kind of familiar to all of you. And then we're also going to use Kloppy and Unravel Sports, which are football-specific Python packages. And I'll do a brief introduction first about myself, then I'll quickly touch on some football data because I appreciate that not everyone knows what kind of data we're going to be using. And then we're going to build, does this work? I need to go here. Okay, this is gonna be kind of bad. Okay, we're going to build a graph neural network expected possession value model using a World Cup 2022 data set, which is publicly available. I've been told it's MIT license, so that's kind of cool. And yeah, we're going to do that primarily with Kloppy and Unravel Sports, and in the back end, it will have a lot of polars. So a little bit about me. I'm a football analytics consultant. I've been doing this for about 8 years, and I focus on deployment of actual research. And some of my research includes these 3 research papers. The graph neural network deep dive into successful counterattacks is republished 2 years ago. And the source code for this was made publicly available, also open sourced. And I turned that into a Python package so that everyone could try and replicate and make a better model than I did. Than we did, I should say. Then I published some work on measuring pressing intensity with the same type of data you see on the right. And then I worked on a paper, and we're still working on this, called the Common Data Format in Football, collaborating with FIFA, the German Federation, and US Soccer Federation, some universities, and some European clubs to come to some data standard, because there's a lot of data providers out there and everyone does it in their own way, JSON, XML, different structures, even though the data is mostly the same. And then I'm also a co-founder and a PySport board member. PySport is a nonprofit, and we want to unite the sports analytics community, get more open source packages out there so people can actually replicate research and connect everything up so that it's interoperable. And I'm also a Kloppy contributor. What Kloppy is, I will share in a second. If you want more info on PySport, we have a website, and in December, we haven't officially announced this yet, but since I'm here, might as well tell you, in December we're going to have a PyData Eindhoven and PySport event where 1/3 of the talks will be sports related. So if you have a project that you want to submit, feel free to keep an eye out for more announcements. So let's get into football data a little bit. There's a lot of different data that's used in the football industry. I will only touch on the event data and the positional tracking data. So event data is sort of a log of shots, passes, defensive actions, where we record the coordinates. We record the player that took the shot or the pass or whatever. We have a timestamp, might know the receiver, and this type of data is generally used to build expected goals models. So that's probably the most advanced thing you'll see on your football score app. And we're also going to be using positional tracking data, and this data is recorded at 10 frames per second. In this case, it's at 25 frames per second. Sometimes it's collected in stadium, but that data is not shared with the public. And there are some companies right now that are collecting this data from broadcast footage, and that's what we'll be using today. Yeah, so the data that we're going to be using is World Cup 2022 tracking and event data. So it's 64 matches, about 7 million frames of tracking data, and about 100,000 events. And if you follow I forgot to say that, but the QR code links to this presentation. You can click on the link, the pff.com, and it will take you to the World Cup data set. And so what is an expected possession value model? It's basically trying to figure out what is going to happen next. So we're trying to measure, in this case, what is the chance that a goal will be scored in the next 10 seconds, given this situation in the game. So on the right, you see, I think this is a situation from the World Cup final where Argentina ended up not scoring. So this is labeled as a 0, and then, or not scoring in 10 seconds, I should say. And we're going to use graph neural nets because graphs are good at capturing these complex relationships between players, between the ball, between teams, and we can encode a lot of information in them. We're going to create one graph per frame of tracking data. How that looks like I will show you in a second. And then, like I said, we'll label the data such that only the events that, or only the frames that lead to a goal in the next 10 seconds will be positive and the rest will be 0. And we'll do the annotation with event data, which I'll also show. So some existing work out there, actually this vape and expected threat and goals added are, I think all of them are open source. At least vape is like an industry standard for people that want to do the type of modeling that you see on the right using event data. So what it does is it figures out, similarly to what we're doing with the tracking data, if a goal is going to happen in n actions or t seconds, I don't remember which it is, and then you can assign credit to players for making a good pass or a bad pass or progressing the ball up the field. And this is one example. And then there's also positional tracking data research out there, but none of this is open source, where they do really cool stuff like this. Basically trying to, on the right, you'll see this image, and it's a convolutional neural net to predict where the next pass is going to be. So that's more complex than what we're doing right now, but none of this is open source, so that's why I said cutting edge open source in the beginning. So what tools are we going to use? We'll be using Kloppy. Kloppy is a Python package that's powered by PySport, and it started 5 years ago because people already realized that there were like 3 or 4 data providers and all of them had a different data structure. And we wanted a way to standardize this data and make it vendor independent, so you can change vendor or load the same data from different vendors and check the quality differences and all that kind of stuff. So it offers an API for easy loading of data. You can filter data. You can transform it, so you can change the orientation. You can change the pitch coordinates to whatever you like it to be. And then you can export it to pandas data frame or polar's data frame. And these data frames will have the same structure regardless of data provider. And again, I appreciate that not everyone in the room has heard of these data providers. This is like very football industry specific. You might have heard of Hawkeye, for example. These are all the data providers that we support. Some of them are still open pull requests, and some data providers provide free data that people can make research projects with or do other cool stuff with. And all these links work. So if you want to check out some open source data, then you can do that. We'll also use Unravel Sports. So Unravel Sports is the package that I created from our graph neural network research, and it allows creating sort of standardized polars data frames from the Kloppy data, and then we can. The main goal is to create graphs from these data frames. So we create graph structures, and then we can train and validate and predict our models. There's also this processing intensity that I did research on. It's kind of separate from the rest of the functionality. And then I pushed version 1 yesterday just to be able to say that I pushed version 1. But it's you have to do that sometimes. And then we're also going to be using Spektral. Spektral is kind of a niche package, and I think it's not been updated for the last 15 months. But it does what it says it should do. So it's kind of a layer on top of Keras and TensorFlow to really easily work with graph neural networks. So in case you don't know what a graph neural network is, this is kind of how it looks like in football. So we have 2 teams and a ball. And we create node features, and the node features describe things that are related to the player or the ball. So that might be their location, x, y coordinates, their speed. I once jokingly said you could encode the color of the shoe if you cared. So you can add everything and you can put it on each individual node feature. And then we have edge features. They describe interactions between these nodes. So for example, you might want to know the difference in their velocity vectors, like where are they moving to. You might want to simply know the difference in speed. That's encoded in these edge features. The adjacency matrix will tell you which nodes are connected and which nodes are not. In the case of our research, we found that connecting all the players on one team and connecting all players on the other team and then connecting everyone through the wall was the best architecture solution. And then something that we didn't include in our research, but I included in the package, was global features. So those describe the, let's say, the overall state of a game that's the same for all players. So the time since the kickoff, or how many how much time elapsed since the last pass, or something like that. And then we're going to do binary classification, because why not? This is what the node features look like. If you take one frame of data, and under the hood, it's like a NumPy array. I added some plotting functionality to my package to debug and see what's going on. So we see the x coordinates, the y coordinates. So the rows are the players and the ball. And we see all these features. So we see, for example, the dark red somewhere in the middle says is possession team. So that's the team that's currently in possession of the ball. We encode who the goalkeeper is. We encode who the ball, which node the ball is. And then on the right, these global features. I was thinking about this for a long time, but I didn't want to make like big architectural changes in the backend. But you can simply join the global features to the node features, and it works. So you can. It's really easy. You can add the period. So normally in football data, you have the period ID, which is 1, 2, 3, or 4 for first half, second half, and overtime. And we normalize that, and we add that as a global feature. We add the timestamp since the kickoff. We add the timestamp since the last event, so the last pass or shot. And those are the same for everyone. So those are the global features. And then we have edge features. And this is actually like a shrunken version, because for every connection, you have an edge. And there's like 270 or 280, but it's a bit much, so I just showed a couple. And we include distance between the players, speed difference, difference in angle between the players. So that's two different columns, cosine and sine, for example. And all these features that I showed, except for the global features, those are the default functionality in the package. But you can add your own features, and I'll show in a second a little bit how to do that. And then we have the adjacency matrix, which is the most simple one. Like I said, in the top left quadrant, that's one team, so they're all connected. The bottom right quadrant is the other team, they're all connected. And then row 22 or column 22, that's the ball, and everyone is connected to the ball to make the graph completely connected. When we're actually training, we're shuffling all the data. So the adjacency matrix might look a little bit more like this. And now I'm going to have to, can I just, no. Yep, I can't see this, great. Okay, so this is that playing? No. Okay, so this is what that looks like. This is a slightly different situation than the one that I showed before. You can see that all the, I'll show it again. You can see that all the x coordinates, so all the way on the left, they get darker and darker because everyone moves closer to the goal. You see some twitching in the matrix too, and that's the angle from the ball carrier to the ball. So because that changes rapidly, like you have some twitching going on there. Yeah, like I said, the bottom left is the adjacency matrix. I tried to record a video where it would like randomly shuffle the data for every frame, but I got a headache looking at that, so I just left it unsorted, or sorted, I should say, to spare everyone a headache. Now I need to go back here. A little bit about the model architecture. I'm not going to do a deep dive on this, but this is the default architecture that we used in our research paper that worked really well. Like I said, we create one graph per frame, we feed it to the architecture, and then in the end we make a graph prediction. This architecture is in the package that you can use by default, but you can also use a different architecture if you want. So now we're actually gonna do some data stuff. So we're going to load the tracking data. So we load one game at a time. That's just how the Kloppy package is set up. So you download all the 64 games and you do this for every game. It just happened that I picked England versus France for this example. We have Kloppy, we import PFF. So PFF is one of the data providers. If you want to do a different data provider, you have to just change out PFF for something else. It has a load tracking and generally also a load event functionality to load the event data. and we feed it the location of the raw data, metadata, and roster information. And then this isn't really necessary, but I wanted to show some Kloppy functionality, so you can filter right on top of the data set. And for each game, we don't want any frames associated with the penalty shootout, because that might mean that we get like a whole lot of penalty goals in our data set, which is not really useful. So we filter out only the matches or the frames that are in the first, second half or in overtime. And yeah, so we have 7 million frames in 64 games. Then we feed this into the first functionality of Unravel Sports, which is taking this Kloppy standardized data frame, or data set, I should say, and then converting it into a Polars data set. There are some default functionalities that you can change. Like you don't really have to if the data is good enough. So there's some like thresholds for maximum player speed. Like if your data is a bit noisy, you can reduce the noise a little bit, and you can decide to add the smoothing or not. So what happens under the hood? Under the hood of the Kloppy Polars dataset class, we use Kloppy to transform all the attacks from left to right. So you saw in the images we attacked from, let's say, bottom to top. It's the same thing. Just making sure that all the goals happen on the same side of the pitch. Makes it easier to train, makes it easier for the model to learn what's going on. Then we transform the coordinates. That's also built-in Kloppy functionality, so you can define your own custom coordinate system. One of the industry standards is to have the origin at 0 and then do the coordinate system in meters. And then we output it to a Polars data frame, which is also, you can see it at the bottom of the code. That's also built-in Kloppy functionality, so you can define if you want to use it with Polars or with Pandas. And then some additional functionality is if the data provider doesn't provide the speed, we'll calculate the speed, we'll calculate the acceleration. If we don't know who the goalkeeper is, we'll just try and infer that. We infer the ball carrier, so generally in this data, you know who the team is that owns the ball, but you don't know who the player is that owns the ball, so we just calculate for each frame the player that's closest to the ball on the team in possession, and we do some extra checks. And then your output is Kloppy Polars dataset.data and .settings. Now the settings aren't very interesting, but it records the orientation and the coordinate system just for sort of future reference. And this is, I'm gonna have a bad time again here. Yeah, this is your Polars dataset that you get out of it. You can see, so we have 1 row per player per frame. So we have like 23 or 23 rows per frame. We record the ball state, so if the ball is out of play, we can filter that out. We have player IDs, we have X, Y, Z coordinates, team IDs, a whole bunch of stuff, velocity, acceleration, and their components, and then if the player is the ball carrier. So this is what we're going to use. We don't have any labels yet, so it's kind of bring your own labels for this data set. So this is all really easily done with the package, but like labeling the data, you have to sort of do that yourself. Luckily in this case, we have event data, and this event data tells us when a shot happened, in which frame, if it led to a goal, if it didn't lead to a goal, if there was a pass, if the pass was complete. Unfortunately, this PFF data is not yet supported in Kloppy, so there's an active pull request that people are working hard on, but I didn't actually need all that much functionality. I just needed the frames, the shot type, or the event type, I should say, and the result for this specific labeling situation. So we join back, we join these frames and these events to the tracking data, and then we figure out if a shot happened in the next 10 seconds. And unfortunately, we only have like 172 goals in the World Cup. So our data set is a bit short on interesting information, but we're going to have to just run with it. It's the best data set we have, so we have to deal with that. So this is how that works in Kloppy. Might be a bit messy, but you can see we join the events on frame ID. So because we do this on an individual game, we don't have to specify game ID or anything like that. Then we sort it by frame ID, make sure that everything is in order. And so this is where we, in the width columns, we first try to find the row that is specific to a goal. And then we grab that timestamp so we know when a goal happened, and then we backfill that timestamp all the way until the previous goal. So we know for each row the time that the next goal is going to happen. We do the same thing for the team ID, so we know which team scored the next goal. And then once we have the timestamp of the next goal and we have the team ID of the next goal scoring team, we can figure out if the team that's currently on the ball is going to score in 10 seconds. And that's what we do here. And if they don't score or if the other team scores, so some of these models, like the vape model that I showed earlier, actually have a scores and a concedes situation. So you can also make a model to figure out if a team is going to concede, and then they take the difference. We definitely don't have enough data to also do the concedes, because that's like 3 times or 4 times fewer data. Now we're going to do a little sanity check. So I had to do a lot of debugging to get this to work. I messed something up in like some release a couple months ago. So this is why I did a sanity check. On the left, you see the attacking goalkeepers. So we're attacking left to right. And if you plot the goalkeepers, then you generally have a good idea of where the team is. So on the left, we have 2 teams, both like their goalkeepers once they're attacking, and the green dots are the goalkeeper locations for when they're defending. The red dots and the gray dots are the ball locations. So I took out all the other players because for a sanity check, it doesn't really matter. And then on the right, we see the same situation, but then for all the frames that led to a goal in 10 seconds. So we see that all the attacks sort of end in the box on the right, and we see that the goalkeepers, the defending goalkeepers in the green, are all on the right. So we sort of know that what we're doing makes sense here. Now, similar to the labels that we added previously, we're also going to add some global features. Like I said before, time since the start of a half is really simple. Time since the last pass or shot, you would do a similar thing as we did before, figuring out the timestamp, the previous action, and then sort of fill your data accordingly. And we're going to add graph IDs. Now, these graph IDs are important for splitting our test, train, and validation sets. We don't want to leak any information from the same game into multiple of these sets. So we split it by game ID. That means that for one game, all data is either in the training set, the test set, or the validation set. You can change that if you want, but it's not recommended. And then we're going to use the Unravel Sports package to actually convert our data frame to graphs. And we do that by feeding it the data frame with the label column. We tell it which columns are the global features. We sample it down. So we had 7 million frames. I sampled it down to 1/5, so 1.4 million. I thought that should be enough. And since 25 frames per second, like the next frame is going to be basically the same as the previous frame. So we can remove some information there without losing anything. You can also specify the adjacency matrix type and the way you want to connect your adjacency matrix. The split by team and ball options are the ones that I shared here. Those are the defaults, and those are the ones that we found in our research to work best. But there are some other options out there that are built in as well. And then we have functionality to add our own node feature functions and edge feature functions. Those are currently set to default, but if you want to add other stuff, you can define your own functions and you can pass them to the graph or the soccer graph converter. For example, we found in our research that acceleration wasn't really helping the model learn anything. If you want to try it and add it, you can define your own let's say, node feature function or edge feature function and pass it to the graph converter to add that as an option. Now that we have our converter ready, we're going to output this data to pickle files. So we use compressed pickle files, 1 pickle file per match. And each frame, again, is 1 spectral graph. So we have, for a single game, we might have like 20,000 or 30,000 graphs. And so those include the node features, edge features, adjacency matrix, and the label, and then also the graph ID. And most importantly, probably, and this was a late addition, is also the frame ID. So if you want to make a prediction, in the end, you want to figure out which frame this graph is related to, and we do that by including the frame ID in each graph. If you want to plot the videos that I showed here, there's also plotting functionality. You can plot images or videos. And so yeah, now we're going to actually train the model. So to do that, we need to initialize our graph dataset, and the graph dataset is basically a built-in Spektral dataset type where we add some additional functionality to make our life a little bit easier. So we add functionality to load directly from a pickle folder or a pickle file, or really easily split our data into test, train, and validation. That's not built into that spectral.data.dataset, but in the graph dataset, that's all built in. So it makes it a little bit easier to do stuff like this. So we have our graph dataset. We've loaded it with, let's say, 1.4 million graphs. And then we can split it. Here I specified a ratio, so 5, 1, 1. So we have a big training data set. We downsample the training labels to make training a lot easier. So as you can see somewhere in the middle, we downsample it so that we only remain with like 39,000 graphs in our data set, but at least, or like 14% is leading to a goal. Makes it a lot easier for the model to learn what's going on. And then we said by graph ID. So we split this data set by the game ID that we provided before. Before we can start training, we also need to create a disjoint loader, and this is built-in Spektral functionality, where for each batch, we create one big graph with, let's say, batch size is 32. We create one big graph with 32 independent graphs that each belong to a single frame, but none of the graphs are connected, so there's no information leaking between these graphs. And that is just a way to do this in Spektral. And we create one loader for the training data, for the validation data, and also one for the test data, but I didn't show that here. And then we actually load our model. So the crystal graph classifier, named like this because there's crystal convolutional layers in there, is the architecture that we found in our research to work very well. So that's built in by default. If you follow this link, you can see how to create your own architecture. And then we compile the model. We use a precision recall AUC because it works a little bit better for heavily imbalanced data sets, which we definitely have. And we get a decent model. It performs about 11 times better than random. It's not great. We don't have enough data. So the research that I shared before, that I showed before using the positional data, they use like 2 seasons. So that's over 700 games of tracking data, and we're only using 64. So we're doing okay, but since we downsampled, we have a really badly calibrated model, and we would like to have more data to make the model better. I made an attempt at recalibrating the model, and as you can see, that failed kind of horribly. Our validation set, which we use for the calibration, has like 10 games of data and only 1,500 positive samples. So it's kind of hard to make the model better. On the left, you can see the normal model. On the right, you can see the temperature scaled version of this, which is still kind of bad, but at least I tried. I don't think I can do better with this data, but that's just lacking. We need more goals, basically. Now we're going to make a prediction, of course, because we have this model. Even though it's not great, we still want to make a prediction. So we load the graph data set again, and now instead of feeding the whole pickle folder with all 64 matches, we just give it one pickle file. In this case, this is the pickle file of the World Cup final. And we create another disjoint loader for the predictions. When you're making the predictions, this is something I found out way too late. You can set the batch size to be kind of big. It makes your predictions faster. It doesn't really do anything for the predictions other than make it faster, but it's a kind of nice hack. And then we end up with our predictions at the bottom. And now we can find, using the frame ID that we recorded for every graph, we can find which prediction belongs to which graph. We create a new Polars data frame, and we can join this Polars data frame back to our Clappy data set that I showed before. And this is, this is kind of what we get then. At the bottom, you see the probabilities of scoring. It's kind of jittery. I think that's because of downsampling. So this is the type of stuff you get. You can do this for a whole game. I didn't want to show this for 90 minutes. So this is actually part of this is a sequence from the World Cup final. Here's another sequence from the World Cup final where the attack ends up in the stand. And so I think it's interesting to see that the graph like sort of changes when a pass is being made. So it's nice to see that gets captured. And then at the bottom or at the end of the sequence, even though the ball gets closer to goal, it like drops off into a cliff. And the reason is because right now the ball's already like 3 meters high. I couldn't show the video, but the model captures the z coordinate of the ball as well. So it's kind of nice to see that. So in summary, what did we do? We created an expected possession value model using Cloppy and using the Unravel Sports package. We use Cloppy to standardize, load, filter, transform, and export our data. And then we used our Unravel Sports package to convert it into graphs. And then use polars and Spektral and Keras for all the actual heavy lifting. Now, if you don't care about football, I don't know why you would be in this room, but if you care more about American football, there's also an American football implementation. And the American football data is like really awesome because they have, every year they have the big data bowl. And they release, I don't know, like 40 games of tracking data every year. And you can do some really cool stuff. This was something I was working on, but I didn't end up submitting it. It's basically trying to predict if the next play, so this is pre-snap, it's trying to predict if the next play is going to be a pass or a run. It's a lot more simple, and you can do it a lot easier because it's basically 70-30 instead of like 0.5%. Yeah, so that was it. Here's a list of really awesome open source Python packages that you can use to do football analytics. And are there any questions?
Thank you.